Now we're going to take a look at the arc length function. The arc length function is s as a function of x is equal to the integral from a to x of the square root of 1 plus f prime of t squared dt. Now let's talk about this a little bit. The dt and the t in the expression for the integrand are really, it's a dummy variable. The arc length function is a function of x, and we see that x is appearing as the upper limit of integration. The lower limit of integration is a constant. For a visual for what this means, we can consider a curve in the xy plane where we have a fixed value on the x-axis of a, and that's associated with a point on the curve. And as x increases, we end up with successively longer arcs. So for an x value here, we would have just this arc. As x gets bigger, we have a longer arc. This should make perfect sense. And so the arc length formula is a function of x, but the integral variable is a dummy variable, and we see that as t. This kind of integral has been presented before. By the fundamental theorem of calculus part 1, if I differentiate this function and write down ds dx, then what I will get is the integrand, the square root of 1 plus f prime of x squared. You see the integrand is now evaluated at x, the upper limit of integration. Another way to write this is, of course, the square root of 1 plus dy dx squared. Remembering again that first derivatives act like fractions, we can rewrite this equation as ds is equal to the square root of 1 plus dy dx squared. Made that a little long, hang on. Dx. Squaring both sides and distributing on the right, we end up with ds squared is equal to dx squared plus dy squared. So if our equation is given as x equals g of y, a function of y, then the arc length can be represented as the integral from c to d of the square root of 1 plus g prime of y squared dy, which could also be written as the integral from c to d of the square root of 1 plus dx dy, the quantity squared. That's the derivative of x with respect to y, times dy. The point there is we don't always have to ensure that our equations are functions of x. That's going to come in handy in our next example. We're given a function x is equal to y to the 4th over 8 plus 1 over 4y squared as y goes from 1 to 2. Almost neglected the instructions there, which are to find the exact length of the curve. First things first, we need dx dy. We need to square that, add 1, put it into the formula. I encourage you to pause the video so that you can do the work now. If you didn't finish or if you got stuck, totally understandable. If you did, just sit tight. Here we have y cubed over 2 minus 1 over 2y cubed. That's using the power rule on each of these terms. I don't think that's where you might have gotten stuck. But what I'd like to point out here is dx dy it's a difference, right? There's a minus here. And that manifests when we square dx dy as a minus in front of the second term, right? Dx dy, the quantity squared is y to the 6th over 4 minus 1/2 plus 1 over 4y to the 6th. When we add 1, that minus 1/2 then becomes a plus 1/2. And just as squaring a difference gave us a negative in front of that middle term, if I have a positive in front of that middle term, then I can express that as the square of a binomial that has a plus, right? That is a sum. And of course, this is going to be y cubed over 2 plus 1 over 2y cubed. the idea here again is that just as we had a minus before, here we're comparing the fact that, or we're looking at the fact that we have a plus there. So this is a common pattern that we'll see on occasion. And now we have a binomial squared, and that's going to fit nicely into the square root for the integral. So I'd like for you to, if you need to, pick it up from here and then finish off the work. So we have in our integrand, well, the arc length is then the integral from 1 to 2 of the square root of that binomial square. And so y cubed over 2 plus 1 over 2y cubed dy. Again, using the power rule, we're going to integrate both. So we have in our integral, and we end up with L is equal to y to the 4th over 8 minus 1 over 4y squared, evaluated from 1 to 2, our original limits on y. Evaluating at 2 gives us 2 minus 1/16. Evaluating at 1 gives us 1/8 minus 1/4. Taking the difference of those pairs, we end up with our exact answer of L is equal to 33 over 16.